Here's some coffee. Say I use 1 teaspoonful, have a cup of coffee in the morning and use 1 heaping teaspoonful, but I decide to cut back. So instead of having the whole amount every day, on the second day I have less, and the third day less still, and so on. And my question is going to be, how much coffee would I use in total? Now, this setting can be used to develop your mathematical sense. And I want to show you. Here is one cutback scheme. On the first day I have a full heaping teaspoonful. So I have 1, and then I add to that the next day 1/2 of a teaspoonful plus 1/4 next day, and plus 1/8, and so on, like that, indefinitely. So my question is going to be, what does that add up to? And you might say, well, it depends how long you keep it up. And here's the first mathematical point. It's true that I might only keep this up for a week or two or a day or two, but I want to look at what would happen if this went on indefinitely and never stopped. So I'm first give it a name, call it S for sum. What is S if that goes on indefinitely, never stops? Well, it takes on a life of its own, and I want to show you that the answer isn't very difficult to find. Here, let this be the amount of coffee. And on the first day, I'll put a 1 in teaspoonfuls here, 2, 3 in teaspoonfuls, the amount of coffee. And the first day there's 1 heaping teaspoonful, and then on the second day there is 1/2, so I come up to there after 2 days. And then I add on 1/4, so that puts me there. And you can probably see what's going to happen. The next time is going to be in there, and each time I divide the remaining portion into 2. And probably you can see that's going to approach 2. After I go on, keep going on and on, the sum will eventually approach 2. So I claim that this sum here above is exactly equal to 2. First of all, you'll probably agree it can't get more than 2. If I keep dividing what's remaining into 1/2 and go that far, it can't get bigger than 2. And it also can't get smaller than 2 by any amount. So any tiny amount you name, I can get closer to 2 than that amount. So if you let that settle in a little bit, you'll realize it's best just to say this sum, if it goes on indefinitely, is exactly equal to 2. Okay, that's the first mathematical point. But that's not very much coffee. 2 teaspoonfuls isn't very much coffee. And so I might want to say that's too extreme. I want to do some other cutback scheme that's a little gentler. And that's going to be B. I want to try a different cutback scheme and see what happens there. And here's where the surprise enters. Okay, B. Instead of having 1 plus 1/2 plus 1/4 plus 1/8 and so on, I'm going to start off with 1 teaspoonful, and then I'm going to add to that 1/2. And then on the third day, it'll be 1/3. Fourth day, 1/4, like that, and so on. Plus a 5th, plus a 6th, plus a 7th, plus an 8th, plus dit. So what does that add up to? First of all, I'm going to give it a name. I'll call it R, something different. What is R equal to? The surprise is R is infinite. So it's larger than any number you can name. And I want to show you that. It's a bit of a surprise, but I can actually prove that to you. But before the proof, I want to show you what happened in the actual physical case. In the actual physical case, if I put out coffee, even if I took a whole teaspoonful, whole heaping teaspoonful, every day and didn't cut back, and I lived to be 1,000 years old, there would only be 365,000 heaping teaspoonfuls, and be a pile about that big, I think. I can show that because a heaping teaspoonful is probably something like a centimeter by a centimeter by a centimeter. And in a meter, there are 100 centimeters, a meter by a meter by a meter. 100 times 100 times 100 is 1,000,000. 365,000 is about a third of that, so it'll be a pile about that big. So that's what would happen in the actual physical case, only a pile that big. But in the mathematical sense, this, if it went on forever, that's where the surprise is. This would add up to more coffee than the whole cabin, more than the whole world, more than anything you could name. So I want to prove that. Okay, first of all though, I would ask you, what about this sum? What about 1 plus 1 plus 1 plus dit? What does that add up to? I hope you see this is infinite. This is infinity, larger than any number you can name. Just go out far enough, and you can always add one more to it, so it's infinite. Okay, what about 1/2 plus 1/2 plus 1/2 plus dit, never stop? What would that equal? Mull it over. I hope you think it's also infinity. It is also infinity because I could group them like this. That's 1 and that's 1, keep on, same as the above. So they're both infinite. And that's what I want to do with our sum R, our infinite series R. I want to group the terms so that each term is at least a half. There, that's at least a half. That's a half. And then I group them like this. I get the next two here. And the smallest one of these two is a quarter. 2 times a quarter is a half. So this is bigger than a half. That's greater than a half. And if you go slow and think about it, I'm going to take the next 4 of them, take up to here. The smallest one is 1/8. There are 4 of them. 4/8 is a half. So this is bigger than a half also. And then I take up to 1/16, and then 1/32, so on like that. And each one of those collections will be greater than a half. So I claim that the proof that R also equals infinity. Okay. So what's we made of all this? Well, an infinite series can add up to something simple like the number 2. Or it can be infinite, depending on the pattern of the series. And they're good to get to know.